For the longest time, we've had this dream of a machine that could do more than just calculate. A machine that could actually reason about the weird, abstract world of math. One that could discover, prove, and maybe even understand. Well, today, we're going to dive into how that dream is becoming a reality, moving right out of science fiction and onto the cutting edge of research. Let's get into it.
So here's our roadmap. We'll kick things off with that grand old ambition to automate all of math and the huge wall it smashed into. Then, we're going to look at two very different modern approaches, the super-focused specialists and the broad, powerful generalists. After that, we'll see why just getting an answer isn't good enough, and we'll take a look at the leap to perfectly rigorous formal proofs. And finally, we'll peek into the future, the AI research co-pilot.
Okay, so where did this whole thing even start? Believe it or not, the idea of a thinking machine is way older than the computer itself.
Yeah, it all goes back to the 1920s and the legendary mathematician David Hilbert. He had this incredible dream of a single, perfect system to formalize all of mathematics, where every single truth could be proven step by step. Now, that grand vision didn't quite pan out, but man, it lit a fire. It inspired the very first AI programs built for one thing and one thing only, to prove theorems.
But these early programs immediately hit a brick wall. See, as a math problem gets more complex, the number of possible logical paths just explodes. It's called the combinatorial explosion. It basically meant that trying to search through every single possibility was just impossible. The computers couldn't handle it. So the dream kind of stalled out.
And that brings us to the modern era, and our first major approach. Instead of trying to boil the ocean and solve all of math at once, researchers started building AI tools that were absolute masters of one very specific thing. This chart nails the two competing philosophies perfectly. On the one hand, you've got the specialists. Think of these like a master surgeon's toolkit. Each tool is highly specialized, incredibly good at one specific job, but you wouldn't use a scalpel to hammer a nail. They're built for narrow tasks and don't need a ton of data, but they take a lot of human expertise to create.
So what do these specialists actually do? Well, they're like these incredibly powerful assistants. They can dig through mountains of data to find hidden patterns in something like knot theory, which can then guide a human's intuition. Or they can hunt for those really weird, clever counterexamples that can blow a long-standing theory right out of the water. And the power here is, honestly, it's staggering. There's a system called Alpha Geometry 2. A specialist built just for Euclidean geometry. They can now solve problems at the gold medal level of the International Mathematical Olympiad. That's literally superhuman performance inside its own little world.
So this is the key trade-off, right? Specialists are unbelievably powerful. They can get incredible results and spot things humans completely miss. But they're hard to build, and most importantly, all that knowledge it gains in geometry, it's totally useless if you ask it to solve a problem in, say, algebra. Okay, so now let's talk about the other side of that coin. This is the second revolution, and it's being driven by those massive foundation models that, let's be honest, we're all hearing about constantly.
And this is a really huge conceptual leap. See, a specialist model learns how to do one thing really well, but a generalist model, like an LLM, learns something much, much bigger. It learns this kind of global operator. It's not just learning a task, it's learning the pattern of how to solve tasks. It's basically learning how to learn.
And the progress has been absolutely wild. Just look at these scores on university math finals from Peking University. A standard model like GPT-4 barely squeaks by with a passing grade. But these newer models, the ones enhanced for reasoning, they're scoring in the high 80s and even 90s. They're acing university-level math. And here's a super fascinating little clue about how these AIs think. When they're tested on PhD-level stuff, they're at their best in these really abstract, symbolic areas like algebra, but they struggle more with things like geometry and topology, things that often require a bit of spatial or visual intuition. Kind of interesting, right? But this is where the story gets really interesting. Because look, getting a great score on a test is one thing, but producing a mathematical proof that is 100% absolutely undeniably correct, that is a whole different ballgame. So, let's just ask the big question. A 94 is an A+, and that's fantastic for a student, but math research doesn't work that way. It demands absolute certainty. So how can we ever trust an answer that comes from a model that's, based on probability? How do we know it's right?
And just to be clear, this isn't just an AI problem. Humans make mistakes, even the experts. These are real examples of errors that slip through peer review in the world's top math journals. One mistake from 1994 wasn't caught for years. Another paper from 2004 was just retracted after nearly 2 decades. We just need a better system.
And that system actually exists. It's called a formal system. The easiest way to think of it is like a programming language, say something like Lean, but it's built for pure mathematical logic. Every single rule is spelled out, every definition is precise, and a proof written in this language can be checked by a computer with perfect, mechanical certainty. There is zero room for error.
So how does an AI actually use this? Well, it's this really elegant little loop. The AI starts with a goal, the thing it needs to prove. It searches a library of already proven math to find relevant stuff. Then a language model suggests a tactic, which is really just a fancy word for the next logical step. That step gets applied, the proof moves forward, and the whole cycle just repeats over and over until boom, goal reached. And this isn't just a theory. This is happening for real. There was this huge project called the Liquid Tensor Experiment, where they used the Lean prover to formalize a major cutting-edge theorem. And get this, not only did it prove the original work was correct, but the process actually helped the human author find a simpler, even more beautiful version of his own proof. How cool is that?
So, all of this brings us to the future. And it's not about AI replacing humans. Not at all. It's about creating a totally new kind of partnership in the world of mathematical discovery. Yeah, the big vision here is an AI that acts as a true research co-pilot. It's the partner that can handle all the tedious, boring, time-sucking work of checking proofs. It can explore millions of dead ends that a human just doesn't have time for. And that frees up the mathematician to focus on the highest level of creativity, asking the right questions and having those big, game-changing ideas.
But we're not quite there yet. There are still some big hurdles. First, we have to get way better at translating normal, human-style math into that formal code. That's the big bottleneck. We also have to teach the AI that the goal isn't just any correct proof, it's a proof that gives us insight and understanding. And finally, these AI agents have to learn how real mathematicians work, that messy, creative back-and-forth process.
It reminds me of this amazing quote from the mathematician Stefan Banach. He said that good mathematicians can see the analogies between different theories, but the very best ones, they see the analogies between the analogies. And that really gets to the heart of what math is all about, finding those deep, hidden connections that tie everything together. And that leaves us with the ultimate question, doesn't it? The real goal of all this incredible technology isn't just to solve the problems we already have. It's to help us find entirely new ways of thinking. So can AI be a partner in that quest? Can it help us find those deep, profound analogies between analogies? We are just at the very, very beginning of finding out.